Hey guys, welcome back to my channel and welcome back to the mathematical modeling video series. This is the third video in the series, and if you haven't seen the previous videos, I'll leave a link here and also in the description box below, so do check it out. So we were talking about population growth models in the previous video, and we'll be continuing with that in this video. So I remember last time I left you guys with question, and that was about how we can make the population growth model better. So, but before we go to that, let's just quickly see, the population growth model that we discussed last lecture. So we discussed that the population growth model is defined as follows: that dp by dt is equal to a into p, where a is called the growth rate usually. And we also saw that sometimes A is defined as the birth rate minus the death rate. That's also something that people do. And we discussed that the solution to this differential equation is P of t is equal to P naught into e power at. And here, if you actually look at it, P of 0 is the population at the initial time. So that means from whatever time instant you are starting to consider the population growth, the population at that starting time instant is P of 0. And P of t gives you the population size at any particular time t. Now we discussed that this is a deterministic and continuous differential equation model. And we also saw that the graph roughly looks like this. That is exponential. The growth is exponential. If this is time, and this is the population. So I left you with a question after we discussed this last video, because the assumption behind this population growth model that we see here, or this exponential growth model, is that there are no limiting factors, that there are enough resources for everybody in the world, and even as time progresses, there is going to be no resource crunch. That was the assumption we made while this model was created. So that's not a realistic scenario in today's world, right? So the question I posed was, how can this be made more realistic, and how can we bring in the effect that the resource crunch has onto the population growth model? So can the model be made better? So if you think about it, the exponential growth graph that we have, right? It says that even as time progresses and as the population is becoming bigger and bigger, the increasing size of population has little to no effect on the resources. And that's absolutely wrong, as we know. So it would make sense, if you think logically, that as time goes on and the population increases, right? So as t increases and p increases, at some point of time, the increasing population should actually influence the population growth. That means that the growth rate cannot become higher and higher as the population is becoming higher and higher, right? Because of the resource crunch. So in some way, if you think about it, if I were to redraw this graph, it's okay that it's increasing in this exponential manner till some time, right? Till some time, let's say t1. This is the origin. And this is the population and this is time, right? So it's okay, and it kind of makes sense that it's increasing exponentially initially because there are enough resources. But once the population of whatever system we are talking about, once it reaches a particular threshold, right, it can't continue growing at an exponential rate, and the growth rate will decrease and it will almost stagnate, if you think about it. And if you think about it, that's what's happening in today's world as well. Like the time it took the world to go from, let's say 5 billion to 6 billion, and then 6 billion to 7 billion is very different. It took a lot longer from 6 billion to 7 billion than the previous 5 billion to 6 billion, right? And that's because of the resource crunch. So if you think about it, the growth rate will kind of start stagnating, and it won't grow exponentially anymore. And it'll kind of, with time, the growth will be very, very, very little. That's the point I'm trying to make. And this would be an improvement on the exponential growth model. So how do we model this, right? So I'd asked you guys to think about it. Like, it can be done in many ways, but in literature, there is one very popular way in which it's done. And the reason I posed the question last video was to introduce this second kind of population growth model, which is called the logistic growth. Now, the logistic growth rate model is defined as follows. So the rate of change of the population, that is dp by dt. This is the rate of change of population. So this is the rate of change. That is equal to a into this sum term into the population. So if you see from the previous exponential growth rate model, this is what the model was before. Now we've added some term here to the exponential growth model, and this new model is called the logistic growth model. This is a very important model because it actually gives us something more like the realistic scenario, and I'll tell you why. So if you think about this term, right, k minus p of t by k. Firstly, the k here, the capital K, is called the it's called the carrying capacity of the population. So it's important to understand what the carrying capacity means. So carrying capacity can be thought of as the maximum population size that a particular environment or a system can accommodate. And if you think about it, that is actually a very realistic scenario. Because in India, for example, we are already at our carrying capacity, right? And any increase above that is causing a lot of issues on resources, on general human life, finding jobs, livelihood, and so many other things, right? So carrying capacity can be defined as the maximum population size that a particular environment can accommodate. Now, if you explore this function, this k minus p of t by k a bit more, it's essentially telling you that this is kind of the ratio of the population that has been yet to be used in the environment divided by the total population that has been, the total population that it can accommodate. So I'll just break this down into two terms and explain what I mean. So one term is k minus p of t, and the second term is k. So p of t, as we know, is the population size at a particular time t. And we know that k, this capital K, is the maximum capacity of the environment, maximum population capacity of the environment. So k minus p of t essentially represents to us the unused or untapped potential or capacity that environment has with respect to the population. So this term is essentially the ratio of the unused capacity in the population size to the maximum capacity of the population size. So when P of t is a very small number, right? So when the population growth has just started, this effect is almost negligible. So when P of t is small, then k minus p of t divided by k is approximately 1, right? So that means, what does that mean? If you look back, if you put that k minus p of t by k is equal to 1 back in this equation, that let's say if we put this is equal to 1, sorry, maybe I should write this a bit better. So if we say that this is equal to 1, we actually end up with what do we end up with? We end up with the exponential growth model that we were looking at before. And which is why, if you notice carefully, I mentioned in the previous slide that in the beginning, when the resource crunch is not a big deal, the population growth will be exponential. And that's what this function, this k minus p of t by k, that's what it's trying to model. That when p of t is very small, the effect of this k minus p of t by p is very minimal, and it's okay. The growth will be exponential. But as p of t increases, as the population size is increasing, k minus p of t by k, this term has a very big effect on the population growth. And if you see, as P of t increases, K minus P of t divided by K actually becomes small. So that means the growth rate, which was just A before, now becomes A into a small number. So it's less than A. So it won't grow at an exponential rate. It will grow and then stagnate. Now I understand that this might be a bit confusing. So I'm going to explain this a bit further with an example, with the help of this slide. So before, I'm going to say here that maybe I should use a darker color so that you guys can see. So before, it was dp by dt is equal to A into P. Correct? Then we said that, okay, I'm just going to call this equation 1. Now what happened is, I said the logistic growth model is maybe I should write this A into K minus P by K into K into P, and I'm going to call this equation 2. So the P term is the same in both equations. It's only the A term which is varying. So let's just call this whole thing A dash. Okay. So the second equation is now dp over dt is equal to A dash into P, right? And this is the logistic growth model, or that's what we've called it. And I'll tell you why it's called that in some time. So now the only difference between the exponential growth model and the logistic growth model in this representation that I've given is A and A dash. That's the only difference. So now let's look at it. So when let's look at A dash when P is very small. So when P is very small, A dash is in fact equal to A. Why is that? Because K minus P by K is approximately equal to 1. That's the reason. Now A dash need to be a bit, when P is large, A dash is lesser than A. Why? Because K minus P by K is less than 1. Correct? So this is what you need to take home from this discussion. The fact that when P is very small, which means when the time has just started and the population is just growing, A dash and A are the same. That means exponential growth is happening. That's cool. Now when P becomes large, when P reaches closer and closer to this carrying capacity K, then the growth rate slows down and we kind of get a stagnation in our graph. And the solution of the growth rate model, if you guys were wondering, is this. It really, the name, logistic growth actually comes from the solution. And I'll tell you why it's called logistic growth. You guys might be wondering. This function is called the logistic function. Okay, and it has some particular properties which I will discuss when I show you the solution curve of the logistic growth model. Now, the main feature you need to understand is that in the logistic growth model, it's an improvement of the exponential growth model, first thing. Second thing is that we have now accounted for the resource crunch in the form of having this capital K, which is the carrying capacity of the population. So the third thing to remember, that the name logistic growth actually comes from the solution, and this is called the logistic function. Now, if I were to break down this model a little bit more and just draw the solution curve for you, let's say this is P of 0, this is the origin, this is the time axis, and this is the population size axis. So let's say we are plotting the logistic growth rate model solution. So the solution would look something like this. Initially, as the time is less, the growth is exponential. But after a particular time, as the population is getting closer and closer to the carrying capacity, you'd actually get a stagnation, and then it would asymptotically. So this is the carrying capacity K. So it would asymptotically go to the carrying capacity K as time goes on. So this is what the solution curve looks like, and this is in fact the property of the logistic function. The logistic function essentially has the property that when when the population size is less, it in fact follows exponential growth, and when the population size increases, the rate of growth decreases and it kind of stagnates towards the carrying capacity. Now the logistic function has many uses, and you guys can look this up. I won't be dealing with it in great detail because it's not that essential to our field of study. But there's something I'd like to mention here, and this is a way in which people try to remember the exponential growth versus the logistic growth. So the exponential growth is often called the J curve, and the logistic is called the S curve. As you can see here, the logistic growth actually has an S shape, right? And the exponential growth curve usually has a J shape. So this is an important, or just a way in which you can probably remember the difference between the two. And the moment you get the solution curve, you can think of, oh yeah, okay, it will stagnate to a point. Initially, it might follow exponential, and so on and so forth. So I'd like to mention one last thing and then stop this video, and we'll pick off from this point in the next video. So what is a compartment? And this is very important because from the next video, I'm going to be starting with something called compartmental modeling. And we're going to take our first look at disease dynamics, which some of you might find interesting given the current situation of the COVID pandemic and everything. So a compartment, the way I look at it, is essentially your scope, right? So for those of you who have done programming, you will know what the scope of a variable is. Something can have global scope, something can have local scope. If you've not done programming, a very simple way to put it is, if you think of your college campus, right? If I'm only modeling something in my college campus can be thought of as a compartment. And any person entering my college campus will be an external person entering my compartment. And anybody leaving my college campus will be a person leaving the compartment. So a compartment is somewhat like a closed off environment that is essentially what we are dealing with. That is the scope of our model. So now population is one such thing that can be thought of as compartments. Now, if I'm talking about the population of just one state in India, I can deal with that as different compartments. Every state population is one compartment. Now, when people migrate for jobs, cool, there are external people entering that compartment. So that is kind of like the rate of entry into the compartment. Same way, some people might be leaving the state for XYZ reason, and that's the rate of leaving from that compartment. So the birth rate and death rate can kind of be thought of as the entry and exit rates from the compartment. So if I have a compartment of the population, I can think of the birth rate as the rate at which people are entering this population compartment, and I can think of the death rate as the rate at which people are leaving compartments. So this is obviously the natural birth rate and the natural death rate. That means due to natural reasons, not due to any external or random or sudden reasons like the COVID pandemic. That wouldn't be counted here. We actually modeled those in different ways, which we will be starting to deal with from the next video. So I just wanted to mention what a compartment is and the fact that population growth can actually be compartmentalized. And that's how it's often looked at in the mathematical modeling world. So I hope you guys understood the difference between exponential growth and logistic growth, and why logistic growth it's an improvement on the exponential growth and gives a more realistic scenario in the case of the population growth of human beings. And given the fact that we do have a resource crunch and all of that. And I also hope you understood the rough idea of a compartment. We'll be dealing with it in detail in the next video. So I hope you guys enjoyed this video. Please make sure you like the video if you enjoyed it, and share it with people who you think might find it interesting. Subscribe to my channel, and as always, I'll see you next time. Thank you.